All right, more from class 3. I figured go for some completeness here because, there's only so much you could accomplish in a class. So I want to provide you with lots and lots of examples. So here we go. This sample problem 2.6 is desired to determine the drag force at a given speed of a prototype sailboat hull. A model is placed in a test channel. We actually had towing tanks at Coast Guard Academy with a towing tank, which is a pretty neat thing to try to figure out what the drag is on a ship. It's a real thing that people do. A model is placed in a test channel, and 3 cables are used to align its bow on the channel center line. For a given speed, the tension in cable AB is 40 pounds, and the tension in cable AE is 60 pounds. Determine the drag force exerted on the hull and the tension in cable AC. Okay, so what we end up finding here as part of this is that even though we're not really looking at the hull, we're looking at a point that gets represented at point A. And so this is the FBD. And we declare that, and we declare what X and Y are going to be. And we put the forces on there, and I think I'll make them poiple. And so we have, these are all cables, so they're all coming away from the thing. So there's FAE, and then we have a force coming over here. That's going to be FAB. And then we have another one coming this way, and this is FAC. I like to try to go alphabetical order there. And then we have some geometry that we want to worry about. Here's a, this is beta, and then this is alpha. I don't like using alpha because we have that for other things. And I think we have one more force. I forgot. Boom. That's the hull. That's right. That's there's a drag force that's acting onto this. If you can imagine, those forces are acting on there, which results in a pulling onto the joint that's right here, right? And so that's going to be the F. What did I say? They call it FD for drag, right? There's some geometry that they didn't give us, so let's get that out of the way. And I'll color code it. Won't stay with this all the time. Beta is easiest found as the inverse tan of rise over run, which is going to be the 1.5 divided by 4. So it ends up being 20.56 degrees. And then alpha is going to be the inverse tan of let's see, opposite over adjacent, that's going to be 7, rise over run, whatever, over 4. And we end up with 60.26 degrees, right? So now let's go back and take care of our sum of the forces in the x direction. Sum of the forces in the x direction equals 0. Declare what positive is going to be, and taking a look at this, we see that FAB is in the negative direction, and it's going to be the sign. I'll keep it as alpha, it's easier, right? And then in the x direction, plus FAC, and that too is going to be the sign, but this time of beta, and then we have plus FD equals 0. And I could shove some numbers in here. We know this tension. We know this angle. And then we don't know FAC. But we do know this angle is 20.56. And we don't know the drag. I think we're trying to find those two things. So we need those two things. All right. So I'm going to rewrite this. This is me sometimes just trying to get some stuff down on paper. A lot of people like to plug it all in at one time, but I like intermediate numbers. It helps me to keep track of stuff. And I'm going to call that, I just started to draw the circle. This is going to be equation 1. I'm running out of room going downwards, so I'll go over to the side a little bit. And we'll say that the sum of the forces in the y direction declare what upwards is. And we start looking at this thing. We go, okay, well, FAB is upwards. But this time we're going to take the cosine of, that's alpha, right? Cosine of alpha. And then also FAC is also what we're considering upwards. It's really to the side, but what we called y. And that's also going to be the cosine of beta. And then all we have now is FAE. But they told us what AE was going to be, right? So we know that. So let's stick in what we know. We know FAB, cosine of the angle 60.26. And we still don't know FAC. But we do know the cosine of, we know beta, so cosine of 20.56. And then lastly, we do know that this FAE is 60, right? And that would be like 2, right? So we could plug these things in. We plug, did I say that wrong? No, that is not 2. Oh, sorry. I was getting ahead of myself. In this case, we see from the y direction that we're actually able to find what FAC is going to be. We plug all those numbers in and we get 42.89 pounds. And that would be like 2, right? And then, so we want to go plug 1 into, oh, nope. Talking without thinking. Plug 2 into 1. And we get negative 34.73 plus 0.3512, but that's going to be times what we just found, that 42.89, and then plus FD equal to 0, and we find that FD is equal to 19.67 pounds, right? So let's say the answers determine the drag. Yeah, say the drag in here. Okay, so they wanted the drag. So let's go 19.7 pounds, right? And they wanted the FAC, right? FAC, the tension in the cable, and that's going to be 42.9 pounds. And if we were going to be precise, this is actually a vector. And it's completely in that direction. That's the direction that the drag on the hull is going to be. Because the way the phrasing goes, you know, you determine the drag exerted on, right? So that would definitely be in that direction if we were to do a free body diagram of the hull. But this one right here isn't the tension in the cable. I say let's not use that as a vector because the cable tension can actually be split in either direction. You could take a look at E and have the cable tension right here, or just like we just did right there, we found we had split the cable and then looked on the inside. So tension isn't really a direction. It all depends on which side that you take on the thing. And it's a minor point here, but in other classes it ends up making a difference. So that's the reason why I tried to point it out. So that's done. And what do we have? We have another 9-minute video. That's what we have.